Hello students, is I audible?
Yes, sir.
Yes, sir.
Yeah, in the last class I was discussing about the waveform distortion, and we have seen the voltage unbalance also. I mean, how we are going to estimate the voltage unbalance, and what are the reasons why the voltage unbalance will exist in a system. But while studying these definitions or these power quality issues, we have not seen that how we are improvising or you are compensating or you are mitigating the issues, the power quality issues. Okay, we'll try to see those kind of the devices which is used to improve the quality in the next coming chapters. Okay, yeah, in the waveform distortion we have seen like it is a steady state phenomena, and if there is any deviation from an ideal sine waveform, waveform of power frequency principally characterized by the spectral content of the deviations. There are 5 types of the waveform distortion, which are DC offset, harmonics, and then the interharmonics, notching, and noise. I have discussed it in very detailed manner also. Okay. The DC offset is going to occur because of the DC loads, maybe the incandescent light bulb life extenders. May consist of the diodes that reduce the RMS voltage supplied to the light bulb by half-wave rectification. Okay. And there is direct current in AC networks can have a detrimental effect by biasing the transformer core so that they saturate in normal operation. This is one of the problem. Okay, because of when you allow the DC current, this causes additional heating and losses of a transformer life also. Okay, direct current may also cause the electrolytic erosion of grounding electrodes and other connectors, because the DC current which is there is going to flow through the neutral, that will cause the erosion, and that deteriorates the grounding electrodes also. Yeah. Next is the harmonics. We have seen it, the harmonics also, why there will be the harmonics in a system, because of a nonlinear load and because of any impedance changing elements which are been there over a cycle. If there is any impedance change, that will be causing a nonlinear in the currents. Okay, the harmonics are the integer multiple of the frequency components. And how do you estimate the harmonic levels? Is one of the quantities is the total harmonic distortion. We'll try to see this particular thing in the next feature class, where we are discussing about harmonics. Okay, is a measure of the effective value of the harmonic distortion. Okay. This total harmonic distortion is not going to evaluate how much is the distortion, how much is the waveform distortion. This is going to, the total harmonic distortion is going to evaluate the effective value of the harmonic content with respect to the fundamental component only. Okay, maybe in the THT, the DC component may be there also. In meantime, I just give about the equation. How do you estimate it? You all knowing about it also, because most of our power electronic codes where we have been talking about the THT, generally the THT is equal to the V square minus of V1 square by the V1. This is somewhat okay. Otherwise, like it goes about the VDC square plus V2 square if there are any even harmonics, and so on by the V1. Okay, this way you'll be evaluating the total harmonic distortion with respect to the voltage or current also, or current also. Okay, this gives about the effective harmonic content in a system. Yeah. And this is a, if you see the second point, periodically distorted waveforms can be decomposed into some of the fundamental frequency and the harmonics. Okay, and the harmonics. Harmonics distortion originates in the nonlinear characteristics of the devices, nonlinear characteristics of devices and loads on the power systems. Okay, and if it is a nonlinear with respect to the voltage and the current, we'll be calling it as a nonlinear also. And regarding the imposition of the voltage and the harmonic current imposed here, when you see this particular waveform, this we have been imposed a third harmonic waveform over here. Okay. In that case, the waveform is going to look like this particular waveform when you're imposing the fundamental voltage or a fundamental current with respect to the a third harmonic signal. Yeah, the interharmonics, we have seen this. There are a non-integer multiples of the frequencies. They can appear at discrete frequencies or as a wide band spectrum. Wide band spectrum in the sense like when you're using a PWM kind of a switching mechanism in a power converters. In that case, we'll be having a wide band spectrum also. Those also yielding to a interharmonics in the voltage also. Okay, interharmonics can be found in networks of all voltage classes. All voltage classes. This is nothing but even in the transmission level. If you have an HVDC system, in that case also we'll be having the interharmonics. But as such, like in the transmission network, we have been using a high quality filters where it won't be allowing this the interharmonics into a system. Okay, the main sources of the interharmonic waveform distortion are static frequency converters, cycloconverters, induction furnaces, and arc devices. Especially when you are talking about the induction arc furnace and arc devices, these are the loads which are be changing intermittently. So because of that reason, you'll be having the interharmonics. Okay, even the power line carrier signals can also be considered as the interharmonics. Okay, where we have been transmitting with the any kind of a signal. For that we use a power line carrier signals also. In that case also we'll be having the interharmonics. In power system, as the varying interharmonic frequency becomes coincident with the natural frequencies. Sometimes, it's not all the times. Okay, they have been shown to affect the power line carrier signals and use visual flicker in fluorescent and arc lightning as well as in computer devices. Okay, I mean, whenever we have the coincidence or the resonance of the interharmonic signals, interharmonic frequency component signals with our natural frequency of the system, then we will be occurring the visual flicker in fluorescent and arc lightning as well as in computer display devices. Okay. Those are the things. Only the thing which we can avoid the interharmonics in a system is we need to use a passive filters, much not may not be the active filters which are being used for the interharmonic elimination. The passive filters, in a sense, like L and C combination or L and CR. We have a bypass filter, high pass filter, low pass filter. Those kind of the things which can be used to eliminate the interharmonics. Okay. Whereas harmonics can be eliminated by using about a passive elements and an active elements. Active elements where your inductance and the capacitance are changing with respect to the what to say, with respect to the any kind of a switching operation of a power electronic device. Okay, I mean, yeah, because of that we can eliminate, not eliminate, we can provide a path also. Whenever we've been talking about the harmonics elimination, as I was mentioning in the uh, earlier class also, we are not going to eliminate any kind of the harmonics. We are just providing the low impedance part for that, in order to not to flow from the source. Okay, yeah. Next is the notching, which is current. You can see here the power electronic device when current is commutated from one phase to another. If there is any delay over the transmission of one phase to another, then we'll be having a notching. Is a periodic voltage disturbances. Is a periodic voltage disturbances. Okay. A periodic in you know a periodic and a periodic, right? Yeah, notching is a periodic phenomena. Even the harmonics also a periodic phenomena also. But not in the interharmonics. Since notching occurs continuously, it can be characterized to the harmonic spectrum of the affected voltage. However, it is generally treated as a special case. The frequency components associated with the notching can be quite high and may not be readily characterized with the measurement of equipment normally used for the harmonic elimination. See, you have a spectrum analysis where we can measure the integer multiple of the fundamental frequency components. Okay. Spectrum, I mean, we have a equipment where we can measure the harmonics that is used for to measure the integer number of the fundamental frequency components. When you are trying to measure a notching, it is not possible. It is not readily characterized with the measurement equipment. Why? Because the frequency which the notching occurred, if you measure the frequency of a notching signal, it is quite high. So because of that, we are not able to measure the normal equipment what we use for the harmonic analysis. Yeah. Next is a noise. We have seen that because of the improper grounding connections, we will be having the noise. Right. Noise is defined as an unwanted electrical signals with a broadband spectrum, spectral content lower than 20 kilohertz, 200 kilohertz, superimposed on the power system voltage or current in phase conductors are found on neutral conductors or signal lines. Basically, the noise here, you see here in the point, disturbs the electronic device such as microcomputer or programmable controllers. Okay, I mean, where we are being programmable controllers. For these things, we try to see the synchronize with the zero crossing. Okay, if you have a noise in this in a system, the zero crossing, I mean, what I mean to say that I have given that picture also in the last earlier especially we try to synchronize with respect to this zero crossing of the voltage. Okay, zero crossing of the voltage. Suppose if there is noise over here, maybe the zero crossing is going to occur at this particular point also. Okay, again it starts rising over here, this kind of a signal. The occurrence of the zero crossing is, maybe it is twice also over here also. One point is this, the other point is this. Okay, maybe when you see over here also the noise, if it is there, okay, it goes something like this. This particular point, it has been occurred at 1 and 2 and 3. It has resetted almost 3 times. Basically, that kind of the problem will be there. Noise disturbs the electronic device such as microcomputers and programmable computers. The problem can be mitigated using filters. We can only using the filters and isolation transformers also. The isolation transformers, it won't. There won't be the grounding won't be there in the on the other side of the secondary side of the transformer, or else there won't be any. When you try to measure a signal, the isolation transformer, I don't have a grounding over here. It just passes over that will be occurred on the secondary side. Okay, there won't be, even when you have a grounding also here, it won't have that grounding effect also. And one thing is all over the noise signal which are going to attenuate with it, it has to go to pass to this signal. But because of that, the isolation transformer, we don't have this noise to be present when you go for isolation transformers. And also the line conditioners. Line conditioner in the sense like it is nothing but a filter also. Those things can be used to nullify the noise. Yeah. Next is so far we have seen about the waveform distortion. As I was mentioning in the last class, this waveform kind of a distortion, generally it won't be occurring in the transmission side. That's what I was mentioning, the transmission side. But typically when you are converting to the HVDC system, if you have a HVDC system, in that case you might be having the interharmonics. This is a AC system over here, and we have a AC system. In this case we can have the interharmonics, but we have a very good kind of filters, and we know that the conversion of a DC to AC converter, we know what frequency it is going to operate this particular the inverter converter, or maybe inverter also. In that case they know about the frequency with which we can operate this kind of a converter. We can use the filters over there, the passive filters. It can attenuate. We'll be getting of a pure sine saddle on the AC side. And then, as I was mentioning, like one of the point where you don't have the triplet harmonics much in a system also. Okay, because of some of the transformers where there is ungrounded system over there in one of the side, there may be the grounded in other side also. If you have a grounding on the both the sides of the transformer, then there is a chance of having not a chance, there will be a third harmonic or triplet harmonics. Generally to trap those harmonics, they won't allow the they change the transformer type of the connections also, not to attenuate to the upstream also. In general, in the transmission system or transmission system, we were not going to having any kind of a noise or any kind of the interharmonics. We are not going to see about the grounding kind of a phenomenon also. Okay, there won't be any kind of a waveform distortion. That's what I want to say. The waveform distortion will be quite less. Distortion distortion won't be there in the transmission network. In the distribution system only we will be having a waveform distortion. Because one thing I can say, because the distribution system is a weak system also, whereas in the transmission system you have a huge amount of a power which are we dealing out. It is then much interconnected system, and this one is a we can say a very um, very strong system also. Okay, it can sustain. Yeah, when you compare with the FX, we have a flexible AC transmission system, flexible AC a transmission system, or flexible AC control control transmission system also. Sorry, flexible AC transmission system. Yeah, basically what these devices and what the power quality improvement devices, improvement devices. Okay, I mean, when you see this one, these are the devices which generally used to control the voltage and then the frequency of a system, of a transmission system, and then the power flow control, P and Q control will be there between the two buses, right? Whereas these particular devices, the power quality improvement devices, it is not to regulate the power flow between the two buses, whereas these particular fax devices used to regulate the power flow or the frequency at one of the bus, or the voltage and frequency. One thing is the power flow controller between these two buses, P and Q. Okay, these kind of the things they are going to use. But these are the devices not meant for the power flow control between these two devices. Maybe uh, maybe they try to do was, here you have a power quality improvement devices. I'm just drawing over here one of the device. I just make out this is a source VS, and you have a series kind of a device, and here you have a shunt device. The similar kind of a system will be there in the fax device. Okay, but the functionality here I'm just giving about power quality improvement device. This is the device which is their shunt device, which is try to pump or inject the harmonic current as well as a reactive component of the power. Why it is, instead of drawing this way the harmonics, we are avoiding this. We are just providing the bypass to a required amount of the harmonic current to the load by the shunt device, by this particular device. This we can say it is an active filter or a passive filter also, Okay. See, why I'm just mentioning these particular facts in the power quality improvement devices. The devices looks like the similar. The functionality is different when you go for a fax device, when you go for a power quality improvement devices. Okay, and also the harmonics or the waveform distortion won't be there in the transmission network, because it is a very strong system, and also there is a filters where it has been used to attenuate the, or to, I mean, one thing, it tries to attenuate, trap the harmonics in the distribution its system itself only. It will not going to what do you say, the pass or percolate or to the transmission network also. Okay, it's going to trap over in the a distribution system only. If you see that a transmission system and then the distribution system, I mean, maybe here at this point we can say this is the transmission system and this is generating system. Okay, this is about the distribution system. It is going to distribution system. It's going to uh, have the harmonics at this level only. It's not going to pass through this because of the type of the transformer connection it has been used over here. Okay, I mean, you may be getting about a doubt about how about fifth and seventh and so on. Maybe third triplet harmonics, maybe it's not going to have pass with the type of the transformers. It's not like that. Maybe you have a different types of the winding connections over there in the transformer. Okay, generally because of that reason also there are the cases where your harmonics won't be passing to a transmission system also. Okay, yeah, don't get confused with the you there will be using a kind of a series compensator in a fax device also. Okay, and the same device over there in a power quality improvement device also, but this functionality is different and this functionality is different. You have a shunt device also, you have a shunt compensator. The same thing we have in the power quality improvement device also. Okay, uh, in a fax these are the terms which have been controlling between the two buses. Okay, whereas in the power quality improvement devices what we are going to improve is we are going to improve the source current quality. We are going to improve the source current quality that is nearer to the sinusoidal and balanced also. And one more point is we are going to improve the a load voltage. We are going to improve the load voltage. Okay, if there is any deviations, I mean, here when you see at this particular point, if you see this terminal voltage over here, if you see there is a feeder impedance and there is a inductance. If there somehow this terminal voltage is influence is going to change, then what happened was we use a device. This is the device, power quality improvement device. We are going to improve this particular voltage. This is a load voltage. Okay, the device which is used to improve the voltage is the load voltage only, but not the terminal voltage, but not the terminal voltage. Okay, here this is the device which is used is improve this current, this the source current quality. The load voltage improved in the sense like we are going to make about it nearer to a sinusoidal and a rated voltage. What we expect the rated voltage? We expect the rated voltage and the frequency also to be maintained constant, but this is not in our control also. This frequency control is not in our control because it is the frequency of the grid. Okay, I mean, don't think like in the distribution level uh, the frequency is can be changed also. As such, like the frequency is much what do you say, um, it cannot be altered, because to alter the frequency at the distribution level we require to have a huge amount of the power. Okay, we require to have a huge amount of the power in order to control the frequency. Okay, that is not in our control also. We just control the rated voltage and try to make it in the balanced voltage, rated voltage and the voltage to be a sinusoidal. The power quality improvement devices which are used to improve the source current quality and then the load voltage. Okay, okay, these are the things which you are supposed to know. And in the facts, you just try to, I mean, if you are interested to look into this, please look into fax devices, which is the device used to control the voltage and the frequency, which is the device used to PA and Q control also. Okay, I don't know much about these particular points, but I know about the power quality improvement devices. The source current is used by quality is improved by the shunt active filters or shunt filters, whereas the load voltage is used to improve by the series filters, by the series active power filters, active power filters. Okay, whereas in some of the literature they says like we can use the shunt active power filter also. You can use the shunt active power filter to improve the low voltage, but as such, like when you are trying to use the shunt active power filter in improving the load voltage, this shunt active power filter power level rating is more in what way it is more is when you are using the filter to improve the source current quality, you use a shunt active power filter. These have a rating. Okay, these have a rating maybe of PA. Okay, the shunt active power filter used for the load voltage is PB. This rating of the shunt active power filter to improve the load voltage is very much higher than the shunt filter used for a source current quality improvement also, or the source current quality improvement also. Okay. Yeah, we have another device where we can go for a combined series and shunt active power filter. Shunt active power filter. This is a device used to simultaneous improvement of the source current quality as well as load current quality. Whatever the devices which I am mentioning with respect to the power quality improvements and devices, the same are there in the fax devices also. But when you see the power levels system diagram, it looks like the similar only. It looks like the same only. As such, like there is no much difference between the mm, the power level circuit. The rating wise, the fax devices is a more high power rated than the power quality improvement devices, and then the frequency with which it is operated. Basically, they use for the PWM scheme. Here also we can use the PWM scheme. As such, like there is no much differences there. Whereas in the fax devices, where we have been controlling with respect to the fundamental frequency signals only, fundamental frequency signals only, especially the modulated signal. What I'm going to talk in the fax devices, the modulating signal uh, is a fundamental level, whereas in the power quality improvement devices, in some cases where you are it is not at the fundamental frequency, the modulating signal is not at the fundamental frequency. Okay, we just go through that the comparison. You will be getting a lot of differences between the fax device and the power quality improvement devices. Yeah, this is about the waveform distortion. Next we have is a long duration voltage variations. So far we have seen, like with respect to the distortion. Okay, the distortion is not with respect to the fundamental frequency component. Okay, as we have seen, like the different kind of the parameters or the quantities which is distorting the voltage or the current is because of the other than the fundamental frequency components is distorting the your ideal sinusoidal signal. Whereas in this case of a long duration voltage variation, it is going to disturb the fundamental voltage value. value in the sense like in terms of the magnitude. Suppose if it is a peak of 230 root 2, peak of a 230 root 2 times your sinusoidal voltage, what we expect in our house. I'm talking about a single phase system. If there is a reduction in the peak magnitude, something around 200 into root 2, okay, that kind of a variation in terms of the fundamental voltage signal magnitude only it is changing. In that case, we'll be calling it as a long duration voltage variations. Okay. I mean, you can consider it as voltage variations. Coming back, what is the long duration voltage variations is? If it is varying more than 1 minute, if the voltage variations, if the RMS voltage variations at a power frequency is fundamental frequency, for longer than 1 minute, for longer than 1 minute. This ANSI C84.1 specifies that steady state voltage tolerance expected as power system. They specified, okay. I mean, this is a IEC standard only. They specified the voltage tolerance also expected on the power systems. If the voltage variation is greater than 1 minute, then we'll be calling it as a long duration voltage variations. Yeah. The long duration voltage variations can be either the over voltage or the under voltage. Over voltage in the sense like if it is rated 1 per unit, then over voltage is more than 1 per unit, maybe the under voltage is less than 1 per unit, can we call it a long duration voltage variations. Just a minute. Yeah. One thing, the variations. If you talk about the over voltage in a system, in our case of in our house also, when you see the over voltage, generally maybe may not be in the cities, maybe in the, especially when you go for the villages, in the night times. If there is an induction, if the industrial loads, if they shut down, we see that illumination glowing is very high also. Okay. Maybe it all depends on the load which has been connected at the distribution level. Yeah. The definition wise, it says if there is a variations which are greater than 1 minute, we will be calling it as a long durations. And then long durations are categorized or can be either the over voltage or the under voltage. Over voltage and under voltage, the fourth point which says about the fourth point here, are generally not the result of the system faults. So whenever there is a system fault, it tries to isolate the fault, and then a recloser will be there. It's going to reconnect back also. Okay, these are not the result of the faults. Over voltages, and especially what I mean to say that over voltage and under voltage are not generally are not the result of the system faults, but are caused by load variations on the system and system switching operations. Suppose in general what happened was, suppose if there is a system where you have a feeder impedance and there is a connection. Suddenly, when you all switch off all the loads over which are being connected over this particular case, when you switch off all the loads, what will happen was we experienced a over voltage or a rise also, because the current going through this feeder impedance is very less, and there may be some mechanism where you have a tap changing transformer, it has changed to the some value. When you switch off all the loads, we will be experiencing the over voltage. Okay, the whenever you switch off the loads, and then you have a capacitor banks which are being connected over here, because of that reason also we have been experiencing the over voltage. But in this case, the experience of the over voltage are not because of the fault, is all because of the loads also. Even when you connect the huge capacitor banks over here, suppose the number of the capacitor banks which are to be connected to at this particular point is it is assumed that it is more also. We have been switching the capacitors here. Basically, the point here it is, this is about over voltage and under voltage are not the result of the fault, but are caused by the load variations of the system and system switching operations also. System switching operations in the sense, like suppose some other DG has been connected, some other energy source which is there, which is connected over here also, a DG which is connected over here, that is also causing the over voltage. Suppose if the more the number of the loads are being connected, if you are connected the huge load over here, we keep on loading the system continuously, we are keeping on the loading the entire the system. In that case, it also experiences the under voltage. Whenever we switch off the loads, it's whenever we are disconnecting the loads, we are be sensing the over voltage. Whenever you have been switching on the huge amount of the loads, in that case, suppose in a peak summer, what you turn on all the ACs, right? Maybe in the daytime also, we'll be turning on all the ACs, right? That causes the under voltage. You can see in some of the case where uh, uh, one of the phase get overloaded. In that case, that particular phase which has been connected, the AC may not work also. So we use a stabilizer, but still it may not be used. It may not. Uh, but even in that case, if the one of the phase get overloaded also, the whatever the stabilizer which has been there, it cannot able to boost the voltage to the required level also. Okay. This is also a kind of a switching mechanism, is creating the variations in the voltage, that is a long duration voltage variations is going to occur in a system. It is not because of the fault, it is basically because of the switching operations or switching of the load, and also because of any system connections also. Okay, if you have a DG connection, suppose if where there is a DG is there, suddenly if the DG got isolated, in that case also this bus voltage is going to down, because the huge amount of the power is going to transfer through this the main line. If you have a DG, then the power sharing is done with the two DG and then the source also. If you don't have the DG, then the most of the load is going to share by this source only. Then we will be having the under voltage. Okay, are you getting right? It is just an understanding how the power is shared. Such variations are typically displayed as a plots of RMS voltage versus time. We are going to measure the RMS voltage versus the time only. Okay. Yeah. Yeah. How we define the over voltage? The over voltage is an increase in the RMS voltage, RMS AC voltage greater than 110 percentage at the power frequencies for a duration longer than 1 minute. If the voltage variation is greater than 110 percentage at the fundamental frequencies for a duration longer than 1 minute. These are caused load switching. Example, switching off a large load or energizing a capacitor bank. And if you connect a huge capacitor bank, then we will be seeing that the long duration voltage variations, the over voltage, sorry, we will be seeing that over voltage. Switching off a large load or energizing a capacitor. We can, if we connect a more the capacitor bank also, we will be seeing that the over voltage. The over voltage result because either the system is in too weak for the desired voltage regulation. I mean, here I was mentioning about the distribution system is a weak system. Okay. Okay, weak system. In that case, we'll be having the voltage variations. And also they are mentioning about the one more point, the voltage controls are inadequate. That is snap setting kind of a mechanism, or a capacitors to isolate also, or not having any enough control in the distribution level voltage. Okay, because of that reason also, suppose there are the cases where in a distribution level we don't have a proper mechanism even to isolate the capacitor bank. They try to, I mean, there won't be any proper switching mechanism, control mechanism in order to regulate the capacitor banks also. In that case, we'll be resulting the over voltage in a system. And one more reason is incorrect tap settings on a transformer can also result in a system over voltage. That is a very that is a human error. Because of the human error, or maybe the controller which is performing the tap setting changes. In that case also, we'll be having the long duration voltage variations. Okay, these are the reasons why we have the over voltages. Yeah. Are there any cause? Are there any if you allow these over voltages, what might be the problem? Is there any issue will is going to rise? Then it definitely, because this is every equipment have a specified voltage limit to have a satisfactory performance. Generally, typically, any kind of a system, what they mention, it is 12 plus or minus, rated voltage plus or minus 10%, or plus or minus 5%, or plus or minus 2%. If it is greater than 110%, and for a duration of more than 1 minute, then it got overheated also, because all the loads which are been there, it's not a very constant kind of a power load. It's all a kind of an impedance load. When you say about the impedance load, what happened was, if the voltage has been raised, if you have an impedance load, then current is also going to rise. If the voltage has been raised, the current is also raised. Then the equipment is got overheated. Maybe there is a chance of total, the equipment is going to get damaged also. Okay. Yeah, that is one of the a typical problem which have been associated with the loads when you are the over voltage. Generally, if the voltage variation is greater than, I'm just making out a figure, a very important point over here. Variation of the voltage variation greater than 110% for a duration of less than 1 minute. I'm mentioning here the voltage varies, some of the loads, it's not all the loads, some of the loads, if the voltage change is greater than 110%, if it is greater than 110% for a duration of less than 1 minute, it is the equipment is, some equipments are able to bear that voltage variations also, greater than 110% for less than 1 minute. Okay. Some loads which are greater than 110%, and greater than 1 minute may not able to bear also. Okay, you are not going to have a satisfactory performance, or you're not going to protect the equipment also. Okay. is about the overvoltage. The basic underlined is if it is the voltage is greater than 110% for a duration of longer than 1 minute. These are the causes of load switching, and the reasons because is one of the other reasons are overvoltage result because either the system is too weak for the desired voltage regulation or voltage controls are inadequate. Incurrent tap settings also result overvoltage. Next is the undervoltage. The undervoltage is a decrease in the RMS AC voltage less than 90% at the power frequencies for a duration longer than 1 minute. Undervoltage is less than 90% for a duration longer than 1 minute. These are the switching events that are quite opposite to the event that causes overvoltages. Okay, that causes overvoltage. Load switching on or a capacitor switching off also. Where we are seeing the overvoltage, load switching off and the capacitor switching on, which is causing the overvoltage. But here in undervoltage, it is quite opposite. Load switching on or capacitor switching off can cause undervoltage until voltage regulation equipment on the system can bring the voltage back to within the tolerance values, stay in the value. Overloaded circuits can also result in undervoltage. This also. Okay, overloaded circuits can also result undervoltage. Here we am defining one of the term which is a brownout. Okay, say I can say it's a line outage also. Sometimes they say it's about this outage. The term brownout is often used to describe sustained periods of undervoltage initiated. Sorry, outage is something different. I'm just correcting over here. I thought it is. The term brownout is often used to describe sustained periods for undervolt initiated as a specific utility dispatch strategy to reduce the power demand. Okay, it is basically some kind of a strategy to sustain the periods of under voltages. Okay, it's a kind of a load sharing mechanism because there is no formal definition of brownout and it is not clear as the term under voltage when trying to characterize the disturbances. The term brownout should be avoided also. Okay, as the under voltage is not very so clear when trying to characterizing the disturbances. Yeah. Next is the sustained interruption. This is an interruption, or we can call it as an interruption. If the voltage value is 0 for a greater than 1 minute, then we be calling it as sustained interruptions. Okay, this particular problem which is related to a problem which is related to a fault also, whereas the over voltage, under voltage, long duration voltage variations are not related to the fault, but this particular long duration voltage variation, the sustained interruption, is a reason of the fault also. I mean, clearing of the fault, it takes a much longer time, more than the 1 minute. Basically, the restoration of a power system when there is a fault in the system is not done by the automatically, where the human intervention is required to clear the fault. In that case, we will be seeing this kind of the problem, which is a sustained interruption. The sustained interruption is called a zero voltage for a duration of greater than 1 minute. And this in the utilities they call it as an outage or an interruption to describe the phenomena of similar nature of reliability reporting purposes. Outage as defined in IEEE standard 1 does not refer to a specific phenomenon, but rather than to the state of a component system that has failed to function as expected. Okay, because of that, I mean, the outage has been defined in that. Okay. Yeah. Also, use of the term interruption in the context of power quality monitoring has no relation to the reliability or other continuity of service statistics also. Thus, this term has been defined to more specific regarding the absence of voltage for a longer periods. It's about the sustained interruption. Okay. In the next class, we'll try to see other definitions. Okay. I'm just stopping over here. If you have any doubts, you can ask me now. As per the schedule, the exam is, I said, like it is on the minor examination. Is there on 22nd September, right? We'll try to delay that exam also. Mostly like we'll try to have that exam on 22nd is fine. Huh? Okay, we'll see. Till time is there, right? We'll be getting a. I'll confirm you on Monday, next Monday, about the minor examination. But try to ready for the exam, whatever the content which I have discussed till now. You try to go through that content and be prepared for the minor examination also. You have any doubts? Minor examination will be there in the LMS also. Okay. Have you gone through the LMS Moodle?
Yes, sir.
Okay, please go through that. I will be updating the most of the content there only. Even in the recently, I modified. There is a one thing which is Mark has done. I removed that particular mark. That what do you say? That attribute also, because that attribute is creating to not to allow for the next lectures also. Once you finish the lecture 1, you will be allowed to go for the lecture 2. Something I heard from the BTech student. So that is the reason I removed it also. Okay, you can watch whatever the video which you want it also. Yeah, the next in the next the minor will be most likely to be there on 22nd only. Okay, there won't be any change in the date. Hardly I get 2 classes. I'll try to complete this particular unit. Okay, we have a very limited content to be finished also. Whatever I'm able to finish by 21st, that is on 20th up to Monday. Okay, we will be having the I mean, whatever I finish up to 28th, that will be there for the minor examination. The examination will be there on Wednesday, 22nd. At the exam is at 6 p.m. You want any mock test to have in a Moodle? Hello?
Yes, sir. Yes, sir.
Do you want any mock test to have in a Moodle? Have you taken any minor examination so far in the LMS Moodle?
No. No, sir.
No, sir.
No, okay. What I do was I'll try to configure one of the exam. Mostly the exam, the mock exam may be on 20th. Okay, you can get some kind of an idea how it will be also.
Okay, sir.
Is it fine, right?
Okay, sir.
Yeah.
Yes, sir.
I'll configure up to Monday. The exam may start in the evening around 7:30 to 8:30 will be there. Monday I'm having class, right, from 6 to 7. Okay, you have to take the exam from 7:30 to 8:30. I mean, I'll be given some 3 questions also. It's a normal questions, not the subject related, technical also, so that you get familiar about the I mean, how to upload your papers also in that Moodle. Okay.
Okay, sir.
Okay then. Thank you. I'm leaving the class.
Thank you, sir.